AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you very much. I still have to get used to being introduced by an AI, but good morning, good afternoon, and good evening to everyone. And thank you for joining us for this latest Accelerating Climate Science with Machine Learning talk here on AI for Good. And I'm delighted to welcome Ravi Nanjudia. Ravi's a professor of the Indian Institute of Science in India, and until recently was the director of the Indian Institute of Meteorology in Pune. He's an expert on the monsoon system. He's been studying this since the early 90s, and we're delighted to have him here to talk about this important topic. I was actually interested to note that Ravi got an NVIDIA Innovation Award in 2013, well before it was a cool and trending topic in our field. So I'm really looking forward to hearing about how ML and AI might be able to help us predict and understand the Indian summer monsoon. Over to you, Ravi.
Thanks, Duncan. Thanks a lot for the nice introduction. So can I start sharing my screen?
Please do.
Thank you. So can you see my screen?
Yep, that looks fine.
Okay, so
Perfect.
Thanks, Duncan, again, and a good day to all of you. Since you're in various parts of the world, I would rather use the Indian salutation, which is Namaskar, which is applicable for any time of the day. So what we are going to talk about today is use of AI, ML to predict and maybe understand. Most of my talk will be about predicting the monsoon, and understanding it using AI, ML is a much tougher job, but I hope I have some, that's one thing where we can discuss about the understanding the monsoon using AI and ML. So this is the outline of my talk. I'll start with the importance of monsoons for the Indian subcontinent. Then I'll briefly talk about the physics of the monsoon, which includes the mean monsoon and the variability of monsoon at different scales. Then I'll talk of prediction of the seasonal monsoon, and then various parts of the monsoon. And then we go to intra-seasonal and predicting the daily monsoon, and finally we come to teleconnections, which have a very big impact on the monsoon. So let's start off. Let's talk about the importance of predicting Indian summer monsoon. Well, about 1.5 billion people live on the Indian subcontinent. And for them, about 75% of the annual rainfall over this region occurs during the southwest monsoon, which is the period of June to September. And if you look at monsoon, it has impact on every sector of the economy. It has an impact on agricultural, or that is food grain production. A drought can cause shortage of drinking water. It can have an effect on hydropower generation. Excessive rainfall could also cause floods. And if the space-time distribution of rainfall is uneven, some parts might be getting excess rainfall, the others will be getting drought, which is very normal in most of the years. So it does create a bit of, you could say, losses. Overall, what we could say is that it had an impact on the well-being of the residents of this subcontinent. And it, of course, has an impact on GDP. And therefore, it is imperative that we try to predict rainfall at various scales. So this, I'll now talk about the impact on GDP. Till recently, there would be an impact on the GDP. If you look at it, on the x-axis is the percentage distribution of ISMR, that is the Indian summer monsoon rainfall. And on the y-axis, you have the impact on GDP. And this is the quadrants where the departure of the normal, that is, we have below normal or drought monsoons, then you can see that the GDP growth is negative. And if you look at the first quadrant, you see that when all the blues, which is the years when the rain was plentiful, then there would be a much larger growth. And though we talk of as a mean, the impact is disproportionately felt by common people, as about 53% of the population, even today, earns their livelihood through agriculture. So this is the impact on GDP. Agriculture of the GDP contributes about 18%, but it employs about 53% of the population. And hence the impact of monsoon variability will be disproportionately felt by this large sized population. So if we look at one of the major things that we always worry about in India is its impact on food grain production. And on the, again, the x-axis is the departure of ISMR, this Indian summer monsoon rainfall. And on the left, this time it is the food grain production. As you can see that in the third quadrant, you're always all seeing the negative growth of food grain. That is, food grain actually falls whenever there is you could see a drought. And that happened till lately, till about maybe 10 or 15 years back. And that perhaps could be because of the fact that now much larger proportion of the area is irrigated. And for the last few years, you can see that though the summer monsoon might have been a little weaker, but the food grain production is showing a less of a decline during monsoons when it is a drought or what we call as a bad monsoon year. But we should realize that only 51% of the agricultural land is irrigated. So that means there is a large number who are still at the mercy of the nature, and a weak monsoon could have a major effect for these regions that would be most vulnerable. So you could say in some sense the weakest sector of the population or the strata of the population has the maximum, you could say, an impact because of a good or a bad monsoon. And hence, we need to have a good prediction of the monsoon. And if you look at between the excess monsoon or the weak monsoon, one of the things we see is that there is not as much of an increase in food grain production when the monsoon is bountiful. That's because of the fact that the farmers wouldn't know that it's likely to be a good monsoon. And hence, if we have a long-term, long-range prediction of the monsoon, and a good one of a good long-range prediction of the monsoon, they may be able to use this information much more usefully and invest more on maybe better seeds and maybe fertilizers or etc. etc. So that makes it even more important that we predict monsoons. So this is a quick overview of the monsoon. On the top, you see the June to September rainfall, the distribution. You can see that there are regions, this is, you could say in some sense, central India. This is Bay of Bengal and this is the Myanmar mountains. So there are regions where the rainfall is very high. This is close to the Myanmar mountains. And this is the Western Ghats, where the winds from the Arabian Sea comes in and there is a high amount of rainfall happening here. And as you can see, even the seasonal rainfall, the seasonal mean, a long-term climatology has a very uneven spread. There are regions in peninsular India, eastern peninsular India, and parts of Sri Lanka in the June to September season where there is very little rainfall. And if you look at the seasonal cycle of rainfall, you see that it starts picking up in June, reaches a peak in July and August, and then drops off to September and then becomes very little the rest of the time. So if you look at monsoons, it's not a kind of an isolated system. It's actually part of a global system, which we call as the Intertropical Convergence Zone, or ITCZ. And India's summer monsoon during June to September is nothing but the manifestation of this ITCZ, which this is the January picture where you can see this kind of a belt snaking around the globe. And this kind of, when it comes to India in July, it kind of moves from this position to the northern, or to the Indian subcontinent. So India's summer monsoon is nothing but the manifestation of ITCZ over our region. So coming to the onset of monsoon, it's not that it suddenly starts raining everywhere. There's a gradual transition with the starting around, let's say, 22nd of May, when you have the Thai onset, that's on Thailand. And then it kind of, at the same time, you get onset over Andaman Islands, which is part of the Indian subcontinent or part of India. And then as we go along, around 26th May, it starts moving north westward. And 1st of June, it hits mainland India, which we call as a monsoon onset over Kerala. That is, it's usually on 1st June. And people look forward to it with, you could say in some sense, expectation, because before that, the temperatures would be very high over most of the country, hitting easily about 40 or 40 plus, and sometimes in parts of Rajasthan, this area, it does also reach at times up to 50 degrees centigrade. So as we move further into time, you see that this isoline keeps moving northwestward. And in Mumbai, you get it around 10th of June. And Delhi, I think, is around 1st of July. And it covers the entire country by about 8th to 10th July. So it takes about more than a month or a month and a half to start from the onset near Andaman Islands or over Kerala to reach Rajasthan. So if you look at it, we might think that if it is onset is early, it might be a stronger monsoon. That necessarily isn't true. The date of onset is not related to the strength of the monsoon. And this is the withdrawal of the monsoon. The withdrawal starts in mid-September and retreats over northern India by about early October. And by 15th of October, more or less, the entire part of the country is the monsoon has retreated. Again, I would like to say that neither the date of onset nor the date of withdrawal, there is a high variability in it. Like if you're looking at the date of onset, there is about a 7-day variability in it. And a withdrawal is even more, is higher variability in it. Neither the date of onset nor the date of withdrawal has anything related to the overall strength of the monsoon. So this is the onset phase, the early phase, how it looks in the month of May and June. You can see that in May, mostly the rain is over southern part of India, Kerala, and parts of Karnataka, which is the state I live in. And when we come to June, it starts propagating northwards, and you see much more rain happening in uh, across the Western Ghats or next to the Western Ghats and parts of the Myanmar Mountain. And northern parts of India hardly get any rain, that is Rajasthan and Punjab, they don't get much rainfall. This is what we call as the peak phase of monsoon, which is the months of July and August. And during this period, as you can see, it rains over most of the country. And it rains pretty highly over what we call as the monsoon trough region. Is a high region of high rainfall over northern part of Bay of Bengal and also the Myanmar mountains and of course Western Ghats. There's another region where is quite a bit of rainfall happening is the equatorial Indian Ocean. And you can see that there's a sharp gradient in rainfall west into the, as we go into the Arabian Sea and also over this Sri Lankan region or the Tamil Nadu low region that we look at. So this is the withdrawal phase, that is September, October rainfall. And in September, the rainfall is still widespread over most of the countries, though the magnitude is much less. And there is quite a bit of rainfall happening over the equatorial Indian Ocean and northern Bay of Bengal. And as we can see, the rainfall variations are different across the early and later part of the season. So we need to predict both the early phase and the later phase of the monsoon. That's one of the things that we look forward to know. Okay, if you're looking at the prediction of monsoon, how would it be in the months of June and July and August and September? So that's also one of the things which we have tried to attempt and which also the India Met department also tries to attempt. So as we know, monsoon is variable on both space and time scales and from days to weeks to months and from year to year. So it doesn't remain the same throughout the season, nor does it remain the same from every year. So what we call as the intra-annual variability. Within a season, it shows periods of very high rainfall, which we call as active spells, interspersed with periods of low rainfall, which we call as the break spells. And this variable within a season is known as intra-seasonal variability, which occurs about the period. I won't call it a period, but about a window of about 10 to 60 days. And shorter period of variability, what we call as the synoptic variability, it is kind of the time scale of 3 to 10 days. This could include localized extreme rainfall events, low pressure systems, and which are like lows and depression. There is a large number of these low pressure systems which start over northern Bay of Bengal and move northwestward into India. And what we call as mid-tropospheric cyclones. Quite often these mid-tropospheric cyclones create extreme localized rainfall. For example, if you look at the Mumbai rainfall, which happened a few years back and also in 2005, it was related to the occurrence of a mid-tropospheric cyclone. So when we look at rainfall during weak and strong years, so as we said, it varies from year to year. On the left, you have rainfall in the month of 2002. And on the right, you have rainfall in the month of July 2007. And 2002 was a deficit that it was 20% below normal over the entire country. So you can see there's hardly any rainfall occurring over most of India. And it was kind of you could say isolated to northeastern part of India and parts of Myanmar. But if you look at 2007, which was a pretty strong year when it was about plus 10% of the long-term average, you can see that the rainfall is quite widespread, and especially over what we call as the monsoon, the trough zone, where bulk of the population also lives. And so if you have high rainfall over this region, it is very beneficial for the country as well. Other thing that happens, we talked of year-to-year variations. Now this is subseasonal variations, and it's also important that we predict it. As we just discussed, subseasonal variations are spells of active rainfall, that is when you have high rainfall, and interspersed with periods of low rainfall. So these are 2 years where it's the day-to-day rainfall that you can see. There are peaks and periods of very low rainfall. So these ones which let's say if high rainfall occurs for a few days, we call it as an active spell, and some periods where it is very low, we call it as a break spell. rainfalls. So this is for the year 1975, where the rainfall was fairly good, and this is for the year 2002. And then you can see that those peaks are fewer, and you see get longer periods of very little rainfall. So there are more break spells and less active spells in a good monsoon year, while you have fewer break spells when in the year when monsoon is good. And knowing subseasonal variability is very important. And if you look at dry spells, they could be detrimental for agriculture. That is, in the middle of the season, suddenly if rain stops happening, then it is difficult for farmers to kind of take decisions on what they should be doing. And hence a forecast of about 10 to 15 days would be very useful. Currently, India uses a multimodal ensemble of atmosphere and coupled models to forecast these spells. The skill is, I would still say, a bit modest, beyond about 10 to 15 days. And we also need to know the break spells and active spells, because not only agriculture, but even the reservoir operations, how they can kind of open water in case there is likelihood of a break spell, then they can release water for irrigation and also store it. If they know that, okay, there's a likelihood of active spell happening, then they can store that. And so we need these intra-seasonal predictions. And as I said, the trends to be, the skill is a little lower beyond about 15 days. And if you look at subseasonal variability, or what we call as a subseasonal to seasonal prediction, this is one of the toughest problems. And for that, WMO has come up with a challenge, which is called as the S2S challenge, which includes using AI and ML for improving the monsoon, not just monsoon prediction, but the global prediction on the subseasonal scales, that is from about, let's say, 10 to 90 days, how we can improve the skill. The problem that we find in subseasonal variation is you may have reasonable skill in the very short period, that is about 3 to 5 days. And you may have very good skill in the seasonal month. That is, let's say, if you're looking at 3 to 4 months or over a season, you may have skill. But in between, there is a kind of a predictability desert where the skill tends to be very low. And that's where these forecasts are extremely important. The subseasonal forecasts are extremely important because, as I just said, for at least for monsoons, we need it for almost, let's say, for agricultural operations or for reservoir operations or many decision making that they would like to do. And also it can tell you better evaluation of what the crops are likely to occur. So this is one of the toughest challenges, and the skill tends to be low in this particular, we could say, interval. And is one of the toughest challenge which WM has put forward as the subseasonal, the seasonal prediction. Coming back to even shorter scale systems, which we call as synoptic scale systems. So you have these low pressure systems, such as depressions and lows, which contribute significantly to rainfall. Most of these systems, they originate from Bay of Bengal and move northwestward. The tracks of these systems are related to the active and break spells. So that is kind of, when you have more active spells, they tend to be a little more northward. And when they are break spells, the track of these depressions and lows tends to be a little more southward. While if it is an active spell, then it kind of moves northwestward. And so it's like there's a multi-scale variability that you're seeing. That is, if you see a good monsoon season, there are more active spells, and within these active spells you might get more low pressure systems and depressions, so there is a kind of a multi-scale interaction happening between various scales, which could be from intra-annual or even interdecadal scales to the daily scale or the synoptic scale. Another feature that we see over monsoons is the mid-tropospheric cyclones. So these are like the maximum vorticity at 600 hectopascal. And many extreme rainfall events, such as the high rainfall event in Mumbai, which caused a lot of havoc, occurred in conjunction with such low pressure systems, especially the mid-tropospheric cyclones. So currently, we are using models to predict the short range forecasts with atmospheric general circulation model. They tend to have a pretty good skill for about 3 to 5 days. However, better prediction of the phase and position of intensity production would be much more desirable. And I think this could also be a area where I guess improving the forecast or removing the biases in the forecast and improving the phase of it, it can be a combined effort that could be done, where you take the outputs from the dynamical models and use AI ML techniques to reduce the biases and the errors in the forecasts. So now we come to intriennial variability. That's the variability from season to season. As we said, as we already seen, monsoon fluctuates from year to year. And hence a long lead prediction of Indian monsoon about a few months in advance would be very useful, because then government would know what kind of steps it should be taking. If there's there's a high likelihood of a lower than normal rainfall, then to kind of store food grains or take appropriate steps for water management with a longer lead, that would be very useful for government and other agencies. So as far as seasonal prediction is concerned, India currently does a seasonal prediction for monsoons using statistical and dynamical models. And the skill tends to be pretty reasonable when it comes to this. But I mean, there's always a room for improvement. And I think that's where AI and ML would come in useful. And one of the things that affects the monsoon is the El Nino, which is the warming of the Central Pacific. It occurs with a period of about 4 to 7 years. And we noticed that there's a strong association between Indian summer monsoon and El Nino. There are various mechanisms which have been thought of, but the final word is yet to be done. And I think that's again where AI and ML can play a very major role to see what exactly is the two-way or the causality between El Nino and Indian monsoon, and which could be unraveled using AI and ML. Right now, there are multiple mechanisms which people talk about, but the final word is yet to be said. So if you look at El Nino, whenever an El Nino occurs, you can see these reds, then that's occurrence of an El Nino, and that's when you get very low rainfall. And the blues are when it is La Nina, that is where there is a cooling of the central and eastern Pacific. So now we'll start looking at prediction of AI of monsoons at various scales. So we'll start with various aspects of the mean monsoon, that is the seasonal monsoon. So one of the first things we did was to predict the seasonal monsoon, that is from June to September, a single value for the entire country. And we used a stacked autoencoder. As you all know, autoencoder is an artificial neural network that can learn compressed complex characteristics of data and can be used for dimensionality prediction. And when it comes to a stacked autoencoder, we are kind of stacking them together to form a deep network with input of the previous autoencoder acting as input to the next layer. We have used 3 levels. What we have found is that if we increase more levels, there is not much of a gain. And a little more detail is that we use unsupervised learning for pre-training 1 layer at a time. Then the total network is fine-tuned using the gradient descent algorithm. And we use 3 algorithms to make the actual final prediction. That is, you take these predictors and then use those predictors to predict the strength of the Indian monsoon. So if you look at the identification of predictors, we used an unsupervised feature learning, which for designed stacked autoencoder, and the grid variables were input. Then it used a threshold for feature extraction from internal layers. It should be greater than twice the standard deviation for it to have a proper feature. And finally, once we got these variables, we did a supervised ranking based on their correlation with different categories of monsoon. Here's a kind of a schematic of what happens in our stacked encoder, which is a 3-step method. So here are some results. We used a training period from 1948 to 2000. The data we used was from IMD, and the testing period was from 2001 to 2014. And for other variables such as mean sea level pressure, 2-meter air temperature, and winds at 200 hectopascal, we used data from the NCEP-NCAR reanalysis data. And the actual rainfall which we compared it with was from the India Meteorological Department's, I think it was 1 degree by 1 degree gridded data. And since we had many regions which kind of gave significant, there were many significant regions which had to be combined together non-linearly, then we used tan hyperbolic activation functions to kind of combine these different regions. And we have used predictors as a weighted sum of geographically distant regions. And so we also tried to kind of look at a combination of vectors where we didn't predictors. One way would be just to keep each of them as a separate entity, but then we combined some of them and we found that we could get better results when we combine some of these variables. For example, sea level pressure with a 2-meter air temperature or wind with 2-meter air temperature. It gave us better results than what each of the variable by itself would have given us. So this is the performance of the various combined product predictors. The predictors, when we combine the sea level pressure and sea surface temperature, that is the temperature of the surface, which is also nothing but the 2-meter temperature, we got an error of 2.8%. And individual sea level pressure itself gave me 4 and SST gave me 4.3. And when we looked at combined predictors of sea level pressure and zonal wind, that is the wind from the east-west direction, when we combined it, we got this one error of about 3%, which is very good. And this is how the prediction during the testing period, and you can see that it is pretty good. And these are the actual rainfalls. The big bars are the actual rainfall, and these are the predictors, prediction by indices using SLP, SST, and a combination of them. And you can see that it gives you better results as compared to the individual predictors itself. And this is the prediction using sea level pressure and U wind. So if you look at sea level pressure and U wind, we get an error of about 3.7%, and the SLP and the SST give us an error of about 2.8%. So if we look at the stacked encoder combinations versus other models, SLP itself gave us about, the mean was about 4.7 mean error, and SST gave us about 4.1, and then combinations gave us as good as 3.9. And this was the root mean square error. The Pearson coefficient is about 0.8 for the best forecast that we are looking at. And the Spearman correlation is about 0.74. And what I would like you to note that is most of them have a very long lead prediction. We can do a prediction even earlier than May using these, or for the best predictors and the best forecast we could do it as early as April. And one of them, with sea level pressure, we could do forecast as early as previous year's August. And if you compare it with other models, then from the dynamical model, if you look at these correlations, which is CFS V2, which is the dynamical model used in seasonal forecast of India, is about 0.55, while our model with the lowest mean absolute error and RMSE gives us a correlation of about 0.82, which is much better than what most other the models give. And certainly that means that AI/ML, even using very simple techniques, is able to give us a very good seasonal forecast of the Indian summer monsoon. So this is a comparison with IMD's operational model. So this is the mean absolute error as percentage of long-term period average. So IMD's, that's the Indian Meteorological Department's operational forecast, has about 7%. So they have two forecasts, one starting in, mid-April. The other one is at late May. So that is called as LRF2. And these are the errors that we find. And what we find is that our AI/ML forecasts using stacked encoder gives you much better results than even the current existing operational forecast used by IMD. So then we said, okay, it is important not just to know the single value for the entire region for the entire season. So we said, okay, we'll also do predictions, which also IMD does, that is for an early or late part of the monsoon, that is June, July, and August, September. So this is the rainfall which we get during the months of June and July. And this is the rainfall which we call as the later part of the monsoon, that is August and September. This is the earlier part of the monsoon, which is June and July, and this is August and September. So if we look at prediction accuracy for early and late monsoons, we again use the same 3-level stacked encoder. And we used sea level pressure, SST, and a combination of sea level pressure and SST as predictors in this 3-layer stacked encoder. And forecast of early monsoon was with a slightly larger error than what we got for the mean monsoon, which is at 6.1% in April, as compared to the standard deviation of about 12%. And error for the later part, for late monsoon, that we could do it as early as March, it gave us an error of about 4.9%, when the standard deviation of the rainfall itself is about 14%. So what we can say is the prediction of late monsoon, that is August and September, is superior to that of the early monsoon. And this is how the prediction happens with the various combination of the predictors, and compared with the IMD rainfall, you can see that it's most of the time it's pretty good. This is for the early monsoon years, and this is for periods, and this is for the later monsoon periods. And this is so this is the next thing we did was, it's not just enough that we do a forecast for the entire Indian region, but even on a seasonal scale, we would like to do what is called as a homogeneous rainfall regions of India. So India Met Department divides this homogeneous regions into these, India into these regions. So we have different regions. One is Peninsular India, the Central India, Eastern, Northeastern India. So Northwest India, Central India, Northeast India, and South Peninsular India. These are the various regions for which we try to do forecast, and which also IMD tries to do a forecast for this. So when we look at prediction accuracy, and so we find that the stacked encoder again is better than the current IMD models. So for Central India, the error is 4.1%. For Northeast India, the error is 5.1%. And for Northwest India, it is about 5.5%. The South Peninsular India, we get an error of about 6.2%. So if we compare the stacked encoder with the existing model, you can see these are the errors which IMD model has, and what this is the error that our proposed model has, and you can see that it's doing pretty well. And IMD does its prediction in the month of June, while we can do as early as January or even previous years. So the next thing we try to see is what happens within a season, and try to look for these active and break spells which we talked about, that is periods of extreme high rainfall and periods of low rainfall. So this is the kind of a spatial picture which happens with strong, let's say an active spell, and a mirror image of that happens when you have a break spell. That is, very little rainfall actually occurs over the the central part of India, northern parts of India, and very high rainfall occurs over northern parts of, not central parts of India, when we are looking at the active spell, and this is for the break spell. So if we look at the active spells, it's kind of break spells, you find it's kind of confined to the Himalayan region and other places. And it is important that we know the predictions for active and break spells, because it is important, as we already had discussed, for agriculture and other operations in the country within a season. So this we have already discussed, that whenever there is an active spell, there is more rain, and whenever there is a break spell, there's less. And then years when they have longer active spells, the monsoon tends to be stronger, and years with larger break spells tends to be weaker. So we try to do a prediction of active break spells using CNN. So we used a CNN to identify and predict active and break spells. We use pented rainfall, that is 5-day average rainfall, because the daily rainfall tends to be noisy, and usually we look at a 5-day rainfall average, which tends to be smoother. And So we used a pentad, that is averaged over 5 days. We used that. And the data we used was from 1951 to 2011. And training was done from 1951 to 1990. And the testing was done from 2000 to 2011. And for active and break spells, these were the various regions that we tried to look. We used the core monsoon region. The seasonal monsoon, we had looked at the entire globe and picked up regions which had significant features which we could extract and use it for predicting with the monsoon. The predictors that we have used for active and break spells, these are zonal wind, meridional wind, that is east-west wind, the wind in the north-south direction, and temperature at 200 and 250 hectopascal. We also used mean sea level pressure, 2-meter air temperature, and this is for the region from 20 south to 40 north and 50 east to 100 east. And we have used an additional region which we call as the mascarene high. This is because of the fact that there is there's a strong relationship between rainfall over the monsoon region and the strength of the high pressure area that you get over this area, which we call as the mascarene high. And there is also a relationship which we thought would be useful. So we use the Nino 3.5, which is where sometimes if the temperatures there tend to be high, which is like the El Nino periods, then it could have an impact on the monsoon. So we use these regions with these predictors, and these were combined together again using CNN. And this is what the evaluation of the model shows. We are showing the AUC score and the ROC scores here. And we have compared it with other models such as LSTM and LDA, and also self-organizing maps, which was done by others. We did work on LSTM and LDA, but other groups also have looked at it, that is using self-organizing maps. We find that skill drops significantly, that is from during various with lead, especially beyond 2 pentimes, that is beyond 10 days. And break spells are better predicted as compared to active spells. And normal spells are less well predicted, but generally when we are looking at normal spells, we are not really worried, because what we are trying to look for is an extreme period where there is very high rainfall or very low rainfall. That is what we are more interested in than kind of predicting the mean. So we can say that the extremes are better predicted as compared to the mean, and that's still not a bad thing for us. And these are the ROC curves, and that you can see that true hit rate is fairly high. And this is for active and break spells, and this is the line of no skill. So you can see that you have significant skill, but of course the skill falls off very rapidly beyond 10 days. And I mean, that's kind of known for, that's the problem with the system in some sense. That is why WM has set up this seasonal to sub-seasonal challenge, so that we can improve the prediction at these scales. So we also looked at prediction of rainfall. Up till now, we have been looking at the intra-seasonal variability. Now we are looking at daily rainfall, that is predicting the rainfall on a particular day. And for that, we have used conventional LSTM. We developed a prediction model on daily scale using this one. And for this period, we again used IMD daily rainfall and TRMM, which is a kind of a satellite data which you can get from NASA. And for IMD, because the data is available for a longer period, we used from 1975 to 1996. And for TRMM, we used from 1998 to 2009. And the testing was done from 2011 to 2015. And for prediction, we used rainfall data from the previous 5 days. And what we found was the skill was fairly reasonable for day 1 and 2. And after that, it would kind of fall very rapidly. And these are the various regions where we looked at the skill for the daily rainfall. That is, we take the previous 5 days rainfall and try to predict the next day, and the day after that. So that's what we are trying to do. And you can see that the skill is in parts, let's say West Central India is pretty good. But if you come to South Peninsular India, skill kind of falls, both on day 1 and day 2. Of course, and you can see that for the same region, day 1 has much higher skill or lower, higher, and as compared to day 2. And these are some pictures for your daily rainfall prediction for 1-day lead and 2-day lead. This is the correlation coefficient that you can see. And 1 day you can see that the correlation is much better. And then as you go to day 2, the skill kind of falls off. This is with TRMM data, which we had used for convolutional LSTM. The other model was with IMD data, and this is with 1-day lead. And as you can see that the correlations tend to be better with IMD rainfall as compared to the TRMM. These are the various operational characteristics that we are showing. So we see good correlation over Central India at 1-day lead, but it again, as I said, reduces on day 2. So the true prediction rate is good for Central India, Northeast, West Central India, and Northwest India. So, but other regions tends to be a little lower, as we had seen in the previous table. So this is, sorry, I think this is a repeat. Sorry. And this is a comparison with the numerical model forecast. So we are comparing the Pearson's skill score for day 1 and day 2 or different rainfall thresholds. And this is what you get with the dynamical model, which is the DFS, the global forecast system, which is used by India Met Department, and is very similar to the global forecast system, which is used by ANSWER. And if we look at the comparison of these for different days, here it is given up to 5 days, but we have looked at only for 2 days with our convolutional LSTM. It has good scale on day 1, comparable, which is comparable to what we get in GFS on day 3. Especially at higher rainfall, the skill tends to be a little low. And currently we are using only rainfall as a predictor. It's possible that if we use more variables, this is like a first cut of daily rainfall prediction. We tried using this particular technique. I'm quite sure that if we use more variables and kind of pick up the variable much more systematically, we might get much better skill. So we used another daily rainfall prediction called as the Deep Learning Weather Prediction System, DLWPS. And DLWPS is something that is used to predict weather. And we have used it on a cube sphere. That is, we take the globe and project it onto a sphere. So we call it as DLWPCS. We attempted to predict precipitation at finer scales over the entire globe. And for this purpose, we have modified the DLWPS from just pure temporal mapping to spatio-temporal mapping using predictors. Sorry, that should be predictors, not predators, that could be more multivariate in nature. So that's why we call it as modified DLWPS CS. That is DLWPS on a cube sphere, and this is the modification that we have done. So this is a kind of a schematic of the thing that we have used. So it uses a convolutional neural network with U-shaped architecture. And what we have done is output is predicted at a daily scale, and training is done for a period of 1979 to 2008, and the validation was done for 2009 to 2011, and independent testing was done from 2012 to 2015. So we transformed the data from latLON, that is latitude longitude data, into a cube sphere, which kind of minimizes the distortion in the data, because you are looking at the entire globe, and kind of does away with the whole problem here. So this is a comparison of our technique with other models. This is the ERA5 reanalysis. This is GFS. We are comparing and this is linear regression, and this is the rainfall, mean rainfall that we are getting from our technique. And you can see that it certainly does better than linear regression and as good as GFS. So we are looking at the Pearsall correlation with respect to ERA5, and here we are MLWPS with GFS, and this is with linear regression. It certainly outperforms linear regression and is comparable to what you get with GFS. And one more thing which we also discussed previously was telecollection, that is linkages between monsoon and various other features. Two other features are like what we call as ENSO, that's the El Nino or the warming of the central and the western Pacific. And another thing which we call as, which is also called as the Indian Ocean Dipole. And what we have looked at is the equatorial Indian Ocean oscillation. So in ENSO, there is a maybe in 3 to 7 years, there's a sudden warming over in the central and eastern Pacific. And that seems to have a strong relationship with the Indian monsoon. Whenever there's an El Nino, monsoon tends to be weaker. And equino is also, this is like that in the ocean, we have the dipole, which in certain years, it tends to be warmer in the western region, which we call as a positive dipole. And when it is warmer in the western region, we call it as the negative dipole. And both ENSO and equino are strongly associated with the strength of the Indian summer monsoon. So we used a simple autoencoder for predicting both El Nino and ENSO, and these are the kind of a schematic of what we do. That is, we use an automated predictor and use a feature ranking and predictions by an ensemble of regression. So this is again a picture of what happens in ENSO. You have a warming in this region, and this is the Indian Ocean Dipole, and its oceanic atmospheric counterpart, which we call as the equino. And why it is important to know El Nino is because it not only affects Indian region, but over the various parts of the globe. You can see that parts of US, parts of course, Indonesia, Australia, Africa, all these regions have a strong relationship, both in the winter, that is the December to February, and to June to August. And as far as India is concerned, it has the biggest impact during June to August, when it tends, whenever there is an El Nino, it tends to be dry. That means we have weaker than normal monsoon. So this is the relationship between ENSO and monsoon, which we have already discussed, that whenever El Nino is strong, monsoon tends to be a little weak. So currently, most of them use numerical models or statistical models, or if you look at it, even now, I guess many AI/ML based models have been used to predict El Nino. So we have, as I said, we have used a stacked encoder for this purpose. And this
Ravi,
is
sorry, I hate to interrupt. You, if you could start to bring it to a close in the next couple of minutes, and then we'll have some time for questions.
Sure. I think I'm done. I think I have only one or two more slides.
Okay.
Sorry,
thanks.
but I think I should be done. So these are the various measures when we try to do our ENSO forecast, and this is the correlation with observations. And as you can see, for June to September, it is pretty good, and even month-wise when we do it, you can see that the correlation is pretty good. And these are the other, the F1 score, accuracy, etc., etc. And you can see that it's quite good using just a simple stacked encoder. And this is comparison with many existing models. We tried to compare it with 13 existing models. I mean, I'd like to say that this work was done about 2 years back, and I'm sure models have improved in the meanwhile. And we find that the approach that we have used, this is our model and this is the other models, and you can see that the prediction is much more, I mean, comparable or as good as the other models. Sorry. So this is for equino, and these are the measures for equino. And as far as we know, this is the first model which predicts the atmospheric component of the Indian Ocean Dipole, and we are getting a pretty good correlation for the June to September months. And for each of these months, you can see that it's pretty good. And these are the other matrix for comparison. So in the beginning, I said it's about both predicting and understanding monsoon, but most of the work that we have done is only predicting it. Not much has been done on understanding monsoons using AI/ML. But we know that monsoon is a multi-scale, multi-component system. So we need to use either to unknown linkages. There might be unknown linkages when we have this huge amount of data coming from various sources such as satellites and terrestrial observations. If we use some of these deep learning methods, you might be able to look at new linkages. For example, the ENSO monsoon, which we already know, there might be other linkages which might be at a deeper level, and we might be able to get a better causality of for all of that. So one of the areas could be that we could use a digital twin for more monsoon-related processes. So this is a summary. I'll not go through it again. This is all I like for you to read, and I'd like to acknowledge my collaborators, Mamita, Bipin, and Manbi, and of course all my colleagues and others. So these are some references. So I'll leave you with the summary, and I'll be happy to take any questions.
Wonderful. Thank you very much, Ravi, for that great overview. It's an impressive amount of work there, and a really nice introduction as well, I think, to the importance of the monsoon system that maybe isn't appreciated more broadly. So that was really great. The questions from the neural network, I think, will come in. If you have questions for Ravi, please just drop them in the chat, and we'll be able to pick those up here. In the meantime, I had a couple of my own, actually, on this kind of question that you raised at the end about the learning the underlying physics of the monsoon, and the other oscillations and modes of variability. I was interested, I think, on one of your the slide where you were predicting the seasonal, the timing of the monsoon. You were able to focus on particular regions, particular kind of predictive regions that gave you skill. Are we able to interpret that? Have you been able to kind of use that as a tool for picking these kind of relationships?
Yeah, we tried doing it, but we could try to understand AI was picking up these predictors, and it was doing a very good job, but why it was doing, we still couldn't figure out. I think that's where we need an explainable AI or understandable AI, which could kind of help us. I think that's where I think people like you can help us, because I'm not a data scientist, I'm more of a monsoon man. But I think this is where I think we can get together and try to see what explanations could be there that it's picking up these features. That I think would be very useful for us to even understand this.
No, I think that's a really hot topic at the moment, and I hope there are opportunities, as you say, to improve our understanding, and then that feeds back into the model development and allows us to kind of just get better forecasts ultimately. I was wondering, you've been working on this a while, and you obviously held a very senior role at the Meteorological Center. Are these being used operationally, or are there barriers to them being deployed operationally? And could you talk a little bit about that?
The AI/ML techniques have not yet been used for operationally, at least in India, as far as I know. We have been talking to them, and actually some of the work we did, we have actually shared the code with them, but I think they have their own constraints, so they've not yet made it operational. But I'm sure there's a lot of interest in Ministry of Earth Sciences, which runs the India Met Department and other agencies, and they are looking. I'm sure they are very eager and keen to use these techniques. They are aware of these techniques, and that the power of these techniques, they know about it. But making something operational, I guess it needs a little time. So maybe
of course, no, it does. And you have to be careful. It's interesting to see, the rapid progress that NVIDIA and people are making with data-driven forecasts. I think it's focusing some minds in the large operational centers, and we'll see. There might be some progress soon. Let's see if there's no other questions yet. Okay, well, don't be shy. But I guess a more general question, and maybe actually given the time, we can maybe make this our last one. But just looking forwards, where do you see the most opportunity for further improvement? Do you see it in the timing, or in the braking, or in the other more detailed local predictive skill? And what are you excited about? What are you looking forward to seeing developments?
I would like to see seasonal monsoon seems to be doing quite okay. Of course, there is scope for improvement. As I said, the intra-seasonal is like a predictability desert. You don't get any skill there. And the reason is that, when you look at short-range forecasts, the initial conditions play a very major role. And when you're looking at seasonal forecasts, the longer periods which come from the ocean, they can play a role. But here is kind of a desert in between, where neither this nor that can kind of give you a good forecast. And I think that's where the challenge is. And I would like to see better improvement in the skill of the intra-seasonal forecast. And of course, when we come to short-range forecast, especially on a very localized scale, for example, if I can tell you that Mumbai is going to get a very good, so much of rainfall in the next 6 hours or 2 days, I think that would be a fantastic forecast if you can do, and it can have a major effect.
Yeah, no, that would be amazing, and a real game changer for that, as you say, that large portion of the population that relies on these for agriculture. Well, I think we're at the top of the hour, so I will take that opportunity to
just to quickly interrupt. Sorry, Duncan. We have had a few questions come in from the audience.
Oh, okay.
2 questions come in. I've put them in the chat.
Perfect. Thank you. Okay. So from Uchara, a couple of questions. I'll pick one. So looking the potential use of digital twins, I think that's obviously a big focus in Europe. Are you envisaging application of machine learning on the digital twin?
Okay, it's actually at let's say at a very initial stage. We are kind of talking to the Ministry of Earth Science and kind of urging them to do something equivalent of a digital twin for monsoons, where we put more complex processes into the monsoon prediction, and maybe a little less complex things for the rest of the globe, because monsoon, as I said, is a global phenomenon, and everything else anywhere else kind of affects. But I think there is a bit of a thought going into it to make a digital twin for especially kind of focused on the monsoon. There is a bit of it's still in very early stages to say that, okay, we are going to do it. I'm sure there's a lot of interest in doing that.
Yeah. No, it's exciting. Again, another area to keep an eye on. I know it's late there, so thank you again for your time, Ravi. It was really great talk, and it just leaves to me to thank you again. So thank you very much, and there's virtual applause.
Thank you. Okay, then. See you, everybody.
Thanks, Ravi.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Mm-hmm.